So I've done this, then I got this, and now that I have, I can define the temperature, which is what I'm looking for. So T2, how do I go about getting T2? Well, once again, our magical, I'm going to go ahead and say P specific volume equals RT, and therefore my T2 will be my P2 specific volume 2 divided by my R, all of which I have. So this is 127 kilopascals, was it? Yeah, 127 kilopascals. This is what I just found, 0.709 meters cubed per kilogram. And over here, R for air, the 287. And as long as my units match, this should be all good. So I have kilopascals, and I have that multiplied by meters cubed per kilogram. And I'm dividing the whole thing by kilojoules per Kelvin per kilogram. Kilograms and kilograms. I have Kelvin left up there, then I have kilo, and I have pascals times meters cubed. That's a joule. This is a joule. And then I have a joule and a joule. So I'm going to be left only with my Kelvin. So my answer is going to be in Kelvin, which is good because I'm looking for pressure, temperature, and this is 313.9 Kelvin. And this should check out. Okay, so now we have got one of the things we're looking for. The other thing we look for is the velocity of the inlet. And for this, what we want to do is a mass balance, right, with the control volume. So basically what we do is we grab this guy here, copy that, we copy that, and we say that what is entering here is the enthalpy of my state 1 and the kinetic energy of my state 1. What is leaving here is the enthalpy of state 2 and the kinetic energy of state 2. And that's pretty much it because there's nothing else happening here. This is adiabatic. But it turns out, so, if my energy balance, if I can't create or destroy energy, that means that enthalpy 1 plus kinetic energy 1 has to be equal to enthalpy 2 plus kinetic energy 2. But as it turns out, the velocity as it comes out is negligible, so this is nil. So really what I'm looking for is kinetic energy 1, which is simply the internal energy, the enthalpy 2 minus enthalpy 1. As simple as that. So all I need to do is grab enthalpy for both states, and if I do that, then I can find the kinetic energy. With the kinetic energy, I can relay that back into the velocity. Okay, so this difference here, if I don't have an ideal gas, I need to go look in steam tables, but if this is an ideal gas, what we can do is relate the C sub P, which is defined as dH dt, as we've seen. So therefore, if I want this, I can just do Cp delta T. Okay, so C sub P delta T, C sub P for air is 1.005 kilojoules per kilogram per Kelvin. Delta T I happen to know because I calculated the other temperature. So this is easy peasy for me to grab. Enthalpy 2 minus enthalpy 1 will be equal to 1.005 times the difference in temperature. It's just 313.9 at the outlet minus 278 on the inlet. And therefore, this minus this equals 36.1. What is a unit? Oh, we need to check the unit. We have kilojoules per kilograms per Kelvin on C sub P, and we have Kelvin or Celsius, doesn't matter, on the difference there. So that means that my unit is kilojoules per kilograms. So kilojoules per kilograms. If I'm after velocity, I don't want to leave it like this, right? I want to actually have this in joules. So obviously this is 36.1 times 10 to the third joules per kilograms. Now what do? Well, we grab this and we relay this back here because it has to be equal. This has to be equal here. So therefore, the kinetic energy is that. And if I want to relate kinetic energy back, I know that this is kinetic energy by itself is mass velocity squared over 2. But if I want it with the mass component there, I need to send the mass dividing. So if I want in that form, the kinetic energy, you can call it kinetic energy over the mass, that's fine. It's just going to be this. Okay, so this is equal to 36.1 kilojoules. So in other words, if I want to find the velocity, what I want to do is velocity will be 2 times the square root of 2 times the kinetic energy over the mass. So the velocity will be equal to square root of 2 times 36.1 times 10 to the third. And I'm taking the square root of this. And this gives me 268.711. Keeps going. So let's go ahead and approximate that to 269 meters per second. That's the inlet velocity that's entering my diffuser. Okay, and to be sure of the units, we always want to be sure of the units. What we're doing here is we are taking, this is actually quite interesting to do. Okay, so let's grab this, or let's grab this. To be sure of what we're doing. Okay, so what's happening here? 2 has no units. But we're taking the square root of kinetic energy, and that is kilojoules, because we left in joules, and then we have kilograms here. So at first glance, this makes no second. This is never going to render meters per second. But, and this is super interesting, we know that a joule is a Newton times meter. We know that a Newton, because of Newton's second law, is just mass times acceleration. So mass is kilograms, acceleration is meters per second squared, multiplying by the other meter there. So this really is meters squared second squared times kilograms. And if I plug this in, and I know that I have a kilogram dividing there, then kilograms and kilograms go away, and I have left with the square root of meters squared per second squared. So obviously this is meters per second, which is exactly the unit of velocity we're looking for. All right, so, and then this is actually quite important, because if you had forgotten about this, right, if you still had this as kilojoules, that would not work. You would still have a kilo here, so that would not work. All right, so I hope this was useful. If it was, consider giving this video a like. If you have any questions, as per usual, just leave them down below in the comment section, and we'll try our best to address them, and we'll talk soon.